Now that we understand congruence, let's return to the addition and multiplication tables and see what that might have to do with subtraction and division. So when we look at this addition table here, we have to think, what is subtraction? Subtraction is the inverse of addition. It means if you add something, you can subtract to get back to where you were. For subtraction, what we need to do is to define something called the additive inverse. So we say A minus B. What do we mean by that? We mean A plus that number, which is minus B. And what's minus B? Minus B is the additive inverse of B. It's the number such that B plus minus B equals 0. That's what it means to be the additive inverse. So when we say A minus B, we really mean A plus minus B. So the question is, do we have additive inverses in this modular arithmetic? Well, to understand that, we just come back and look at this addition table. So for every number here, is there some number we can add to it such that we get back 0? Namely the additive identity, 0. So you see here 0 plus 0 is 0. 1 plus 5 is 0. 2 plus 4 is 0. 3 plus 3 is 0. 4 plus 2 is 0. And 5 plus 1 is 0. So every single number has an inverse. So addition and subtraction are very easy. Whenever we have modulo arithmetic, it's very easy to find the inverse. In particular, minus b in mod m is just m minus b. So here I'm thinking about numbers that are already between 0 and m minus 1. So we have b, some number between 0 and m minus 1. We just subtract it from m, and we'll get the additive inverse. So this is really easy. What about multiplicative inverses? Multiplicative inverses are numbers such that when you multiply by them, if you multiply a number by its multiplicative inverse, you get back the multiplicative identity, which is 1. So do we have multiplicative inverses? Well, we never have a multiplicative inverse for 0, right? Because multiplication by 0 always gives rise to 0, and there's no way to invert that. We've destroyed all the information. There's no way to get it back. So what about other numbers? Now, for regular integers that you're used to, you don't really have multiplicative inverses for most numbers. In fact, you only really have it for 1, right? Because 1 times anything is the number that you multiplied by, and its inverse, 1's inverse is just 1. So 1 has a multiplicative inverse, kind of no matter what you do, namely itself, 1. But everything else for the regular integers doesn't. So 2, for example, doesn't have a multiplicative inverse, because the multiplicative inverse for 2 would be a half, and a half isn't an integer. But let's look over here at mod 6. So in mod 6, 0 certainly behaves the same, and 1 behaves the same. But if you look closely, in the multiplication table for the other numbers, actually a 1 does appear in one place, for 5. Look at 5. 5's multiplication table has a 1 in it. 5 times 5 is 1. Why? Because 5 times 5 is 25. 25 is 1 plus 24. 24 is a multiple of 6. So 5 actually has a multiplicative inverse. So does 1. So in mod 6, it is possible to divide by 5 and actually get something. And you see that here because look at the entire multiplication table for 5. It has every number in it, which means that you can undo multiplication by 5, namely by multiplying by 5. So let's look at see how that works. So 5 times 5 is 1. If you want to undo that and get back the number you multiplied, multiply by 5. Yes, 1 times 5 is 5. Let's take another one. Let's take this 4 right here. This comes from 5 times 2. 5 times 2 is 4. If you want to get back that 2, we can hit this with a 5. So we can hit 4 times 5. 4 times 5 is, in fact, that 2. So it works. But when does it work? This is what we have to really think about. So multiplicative inverses and hence division exist sometimes. Some numbers, mod m, have multiplicative inverses and others don't. So in the case of 6, only 5 and 1 have multiplicative inverses. So what is it about 5 and 1 relative to 6 that is different than, for example, 2, 3, and 4, and 0? So here's where we have to think a little bit. 2 and 6. What is it about 2 and 6? Well, actually 2 divides 6. So is that what it is? Is it about being a factor, of being a factor of 6? Well, certainly that will work for 3. 3 divides 6. But 4 also doesn't have a multiplicative inverse, and 4 doesn't divide 6. So it can't just be that. So what is it about 4 and 6? For 4 and 6, what we notice is that 4 and 6, although 4 doesn't divide 6, 4 and 6 actually share a factor in common, namely 2. And maybe that has something to do with it. So thinking this through gives us a kind of guess. So our guess is that multiplicative inverses exist, A exists, mod m, whenever A and m have no factor in common. So do we have some language, some easier way of saying that A and m have no factor in common? Well, actually we do. We have the idea of GCD, the greatest common divisor. So another way of saying this is that the GCD of A and m, this is the largest factor that A and m share, right? The biggest number that divides both A and m, the greatest common divisor. So we suspect that what's going to happen is A inverse exists when GCD of A and m is just 1, when the greatest common divisor is just 1. So when we say A inverse, again, this is always A inverse exists mod m. So to understand this, to think about this, it's good to maybe explore first before we actually, go out and set out to prove it. So the first thing we should think about is there some special m such that the GCD of A and m will always be 1, except of course for 0, because m and other numbers that are smaller than m won't share any factors. Well, when can that happen? It's pretty easy, actually. If m is prime, then of course m doesn't have any factors besides 1 in itself, and so none of the numbers that are smaller than m can share any factors with m. So that's a pretty good thing to try. Let's try a prime number. Okay, so what I've done here is I've written out the times table for 3. And notice for 3, in fact, you have multiplicative inverses for all numbers. 1's multiplicative inverse is 1, 2's multiplicative inverse is 2. And of course 0 never has a multiplicative inverse. So it works for m equals 3. So let's try m equals 5. In 5, I've written out the times table. Again, notice that every single row is a permutation, except for, of course, the row corresponding to 0. And if you look here, you have 0, 1, 2, 3, 4, so 1 doesn't permute at all, just keeps the same order. But everything else always has a 1, and it's just a perfect permutation. So this seems to be working, right? Our conjecture that you have a multiplicative inverse whenever the greatest common divisor is equal to 1 seems to work, because when we try it for these prime numbers, we get multiplicative inverses for everything. So now it comes time to figuring out how can we actually prove it, and what is it in fact that we want to prove. So the property we want to prove is that there's a multiplicative inverse. But it turns out that we can actually prove something stronger, which is capturing our intuition better, which will also turn out to be useful later. So what is the stronger property we want to prove? The stronger property we want to prove is this permutation property. Which says if the GCD of A and M equals 1, then the multiplication table for A mod M contains all M possible numbers. Right? Mod M, there's M possible numbers, and the multiplication table contains all of them. Namely, that the multiplication table, when you multiply by A, what you get is a permutation of the other numbers. No two numbers get slammed onto the same number. So to prove this, what is it we want to say? Well, we need to look at the multiplication table. What is this multiplication table? It's these numbers. That's the numbers are going to come out. 0A, 2A, 3A, and so on. So we want to say that all of these numbers are distinct. So how do we say that? What we want to say is if XA equals YA, okay, everything here is mod M, right? Mod M. For 0 less than or equal to X and Y, both of them in this range, then X equals Y. So you see why this is the same as the permutation property. It says that if two numbers are the same, they're actually in the same position in this multiplication table. It can't be the fact that two different positions in this multiplication table have the same number. So how do we prove this kind of a statement? So we'll prove this by contradiction. Suppose not. Then X does not equal Y, but XA equals YA, mod M. So XA minus YA equals 0, mod M, which means that there exists a K such that XA minus YA equals K times M, which is the same as saying A times X minus Y equals K times M. So now, let's look at X minus Y. Without loss of generality, let's assume that X is greater than Y. Why? Because it doesn't really matter. We said X does not equal Y. Let's just say X is the bigger one. So then, X minus Y is greater than 0, because when you subtract a smaller number from a bigger number, you get a number that's greater than 0. And we know that x and y, x itself is smaller than m, so x minus y also must be smaller than m. So x minus y can't actually reach m. Now, let's look at it. A times x minus y equals k times m. But a and m are relatively prime. That's another way of saying their GCD is, after all, this is another way of saying GCD of a and m is 1. So a and m don't have any divisors in common except for 1, which means that if you look at this expression here, this guy here and this guy, they share no factors. So the factors of m on this side have to be an x minus y, all of them, which means x minus y has to equal something times m. K prime times m, and a equals k divided by k prime. This is how these things have to line up, because after all, a and m are relatively prime, so all the factors of m have to be an x minus y. But this can't happen, because x minus y is some number that's greater than 0 and less than m. So look at the factors of m. Well, if it's greater than 0, it means I can't use k prime equals 0. That won't work. So k prime equals 0 can't be true. K prime equals 1, that also can't be true. Because if k prime is 1, then x minus y would be equal to m, but we know x minus y is less than m. So this can't happen. Because x minus y can't equal k prime times m for any k prime that's an integer, we've got a contradiction. This contradiction says that this can't be the case, that x can't be equal to something other than y, which means that the claim is correct. So with this claim proved, we know that the only place where you can have two numbers that are the same inside this is in fact at the same position. You can't have two numbers being the same anywhere other than the same position. So that means that we have m numbers, 0, a, all the way up to m minus 1 times a, and they're all distinct. Moreover, these m numbers all come from zero, 1, 2, all the way up to m minus 1. So we have m numbers, all distinct, all coming from 0, 1, 2, all the way up to m minus 1. How many numbers are there here? Well, there's exactly m numbers here. So it must in fact be all of them. That the multiplication table for a has to contain all of the numbers. There's just no way out. You have m numbers, they're all distinct, and they have to come from this set, so it must be all of them. That proves by what's called the pigeonhole principle, that if you have m pigeonholes and m pigeons, and there are no two pigeons are in the same pigeonhole, that in fact all the pigeonholes must be filled. By that principle, we know that we have a permutation. We've proved the permutation property. So once we have the permutation property, we have that multiplicative inverses exist. Because by the permutation property, we know that it contains all possible numbers. So if it contains all possible numbers, it must in fact contain 1, because 1 is a possible number. So from here, we can prove immediately we get the theorem that if the GCD of A and M equals 1, then A inverse exists, mod M. So exercise. Prove that if A inverse exists, mod M, then prove that the GCD of A and M must be 1. And in fact, you can do that by first showing that this implies that the permutation property exists.